Welcome back, everyone. We are to creating power series. So the last video, we said once we have a power series, how do we figure out what its radius of convergence and interval of convergence is? We are now going to create one. And we're going to learn two ways in this class. This lesson, actually, this is only half, this is part 1 of 11.9. There'll be a part 2 later. We start out with the geometric series that we've used before. And we know in a geometric series that it converges to this as long as the absolute value of r is less than 1. Now, what that does is if a is 1 and r is x, you can see that exactly matches that, and we end up with a power series. 1 plus x squared plus x cubed and so on. And as long as x is between -1 and 1, we're good to go. So what it's basically going to be is we need to get this to whatever that is going to equal, I'll put like a red blob, whatever's there, whatever function of x is there, will give us I'll do it the same way. Red blob to the nth power. So if it's just x, it's just x. Now, a couple things that need to be true. It has to be minus. If it's not, we're going to have to do a trick to make it minus. And that has to be a 1. If we have other stuff in the numerator, which we will in a few minutes, we'll find ways of handling that as well. So let's take our first one and our f of x. And I'm going to rewrite it as 1 minus -x squared. And the reason I'm doing that, again, we have to have that minus as a part of that. So here is our red blob now. So this becomes a summation of -x squared to the n. And I'm going to write that a little bit more clear for us. I'm going to take the -1 there and make it its own thing. And then we have x to the 2n power. So this is a polynomial version of that. Now, I'm hoping that you recognize this as if I were to integrate that, I would get inverse tangent. So imagine having a power series, a polynomial representing inverse tangent. That'll be in the next video. Let's talk about the radius of convergence. This here is my r. So let me underline that. And so we need the absolute value of -x squared to be less than 1 in order for us to converge. Well, the absolute value makes it positive, and when I take the square root of both sides, I end up with the absolute value of x is still less than 1. So we're here. Unlike the other polynomials, the other power series, pardon me, we do not need to check the endpoints. We already know that if r equals 1, we have a problem. That it's going to diverge. So r needs to just strictly be less than 1. So our interval of convergence is -1 to 1. And our radius is r equals 1. And we are centered at 0. We can see that here. That's not like x minus 3 or something. All right. Let's do a bunch more. So now we're going to start in with the tricks, the little ways of handling this. You'll notice first off that that's not 1 plus. So I'm going to write f of x like this. I'm going to rearrange it, 2 plus x. And what I'm going to do is I'm going to factor a 2 out of the denominator. So now I do have that 1 with an extra 1/2 on the outside. I'll get to that. We can further rewrite this. So whenever we have a plus in between, like we did up here, we're going to have to do that minus trick. So using our power series rule, I'm going to get a 1/2. There's my 1/2 there from the outside. And this is going to give me its negative, so it's a -1 to the n, x to the n over 2 to the n. And I'm going to further fix this up by multiplying that 2 times 2 to the n to get this here. So I'm going to get 2 to the n plus 1. And here is our power series representation. And I'm going to note in this case that to find the radius, or interval of convergence, I need the absolute value of -x/2 to be less than 1. Again, the absolute value gets rid of the negative, not an issue. So we end up with -1 x/2 and 1 multiply through by 2. So our interval of convergence is -2 to 2. Radius, which it doesn't ask for, but that's okay, is 2 in this case. Not too bad. Just a new way of thinking about stuff. All right. Notice we don't have a 1 in the numerator at all in this case, and that's okay. What I'm going to do is in the denominator, I'm going to factor a 3 out. So I'm going to have a 2/3 on the outside. So f of x is, I'm going to have 2/3 times 1 over 1 minus x over 3. And I know I did several steps at once there. So again, I factored out a 3, that makes it x over 3. That's a 1. And then I pulled the 2 out also in front. Now I can clearly see what r is in this case. That's the x over 3. Notice there's no -1 in this case. All of these other ones we've done so far were plus. So we end up with a -1 to the n in the answers. This one we do not, it's already minus. If you remember, it needs to be minus. So if it's already minus, then it's just the positive version of it. So this becomes x over 3 to the n. And what's going to happen is that 3 is going to be brought in to make that n plus 1. And the 2 does not get an n. Two x to the n over 3 to the n plus 1. There is my power series representation. So let's talk about the interval of convergence. There's my r. That has to be less than 1. And then multiply through by 3. So our interval of convergence is -3 to 3, with a radius r equals 3. Not too bad. Let's keep going. All right. Now this one, we sort of already did the x plus 2 right here. And what I'm going to do is rewrite f of x like this. And I'm going to use the previous answer that I got for that. We already did the 1 over x plus 2. So this is going to be x cubed times the summation -1 to the n, x to the n, over 2 to the n plus 1. And all that's going to do for us, and by the way, this will have the same interval of convergence and radius as this one. That won't change. However, what I can do here is that x cubed, I can bring it in and add it there. And here it's n plus 3 over 2 to the n plus 1. And there is my power series representation. And from example 2, we know that the interval of convergence the radius r equals 2. All right. So next up, example 5 here. I'm going to hold off that x squared off to the side, so f of x. And I'll bring that in at the end. And I'm going to rearrange this to look like this. Whole lot going on with that one. So there's my r. So I'm going to have x squared over 16 times summation n equals 0 to infinity. Now, because it's plus, we're going to have that negative 1 to the n. X to the 4n over 16 to the n. And I'm going to bring in the x squared to here, make it plus 2, and then plus 1 down here with the 16s. So negative 1 to the n, x to the 4n plus 2, that's from here, plus 2, over 16 to the n plus 1. And that is my power series. It represents that crazy function. Again, remember, this is just a polynomial representing this function here. So to find the interval of convergence, here's my r again. So it needs to be less than 1. Absolute value takes care of the negative, no problem. So negative 1, x to the 4th over 16. Let's keep it in absolute value form for now. So that's going to give us x to the 4th absolute value is less than 16. And when I do the 4th root, it's going to stay absolute value of x is less than, and 4th root of 16 is just 2. 2. Which means this is my interval of convergence. With a radius of 2. So not too bad. We have one more to go. And whenever we have the same degree or a bigger degree on top, we need to do long division. So I'm going to go off to the side here. In fact, I'll utilize some of this space here. And that's going to give me a 1, x plus 2, subtract. That gives me negative 3. So I'm going to say that f of x is now 1 minus 3 over x plus 2. And in fact, I'm going to say that this is 1 minus 3 times 1 over x plus 2. And once again, we've already done this one. So we have that. And I'm going to get a little fancy here. I'm going to bring the 3 in, which it will not have an n power. And I'm also going to bring the minus in there. So we get this 1 plus -1 to the n plus 1. So I took that -1 there and I brought it there times 3 x to the n over 2 to the n plus 1. So it's a little extra fancy here. That again is an x. And if this is going to have the same as the example 2, right? The interval of convergence, -2 to 2, with a radius of r equals 2. And that is our first way on how to create a power series. Kind of cool. Thanks a lot.